Alright, time for another draft. Physics.com, debatephysics.com also. And, alright, so Ian Gosling has done another experiment. I really don't understand his point or his argument because nothing much is illustrated in what he did. But it is curious as an experiment, I suppose. So this is where it starts. Now, this image is interesting to me, just because, we have a nice center line from this string dropping down. And I was just thinking, if you took this object and swung it over to this side, you see this little bit of change in distance, and it looks an awful lot like the results you got from the lever. And that was only supposed to be twice the height. And so 4 times the height is looking like, if I switch these angles, this would end up coming down here, and so, just go by distance from this center, and I put this here, it's looking an awful lot like that anyway. So, just saying. So he's crashing these two things into each other that aren't very elastic. I mean, they don't bounce off each other well at all. So it doesn't tell you much. From all I can observe is that the 1.5 mass from 4 times the height does stop, it appears, just because it becomes in focus. So I'm just going by the fact that you can see it in focus. It's not blurry after the collision. And the other one does move a little bit. But what Ian doesn't get, okay, first off, the amount of energy it takes to move something on this horizontal plane is a tiny amount. You could just tap something and it'll move very far down here. Up here, it's really hard to move stuff up higher. So if you had a little fan or something and you were going to move the object with the fan with a constant amount of force it was applying, you could make the thing move a lot further here with the same energy than you can go here with the same energy. This takes a lot more energy to go that way when you're higher up. So the higher you are, the harder it is to push the object higher. And the lower you are, the easier it is. So the distance is a lot less force required to go 3 inches here than to go 3 inches out here. A lot more. All right. And then the obvious thing, okay, is these giant poles. That just ruins the whole experiment. So it's the dilution argument again. He's not recognizing that you can't do the experiment. This isn't an ideal lever again. It's way short of ideal. These are probably just steel, hollow steel, so they probably don't weigh a fortune, but they weigh at least as much as the masses, maybe more. And their momentum is what's colliding. So when he's doing the experiment, I'll show it. There's not much to it. He's not claiming anything either, which is just really kind of bizarre. So I don't even know why he's sort of bothering. Somewhere in here should be
pretty much together. Okay, let's see how it goes.
Yeah, let's see how it goes.
What? 3, 2, 1.
I wasn't able to stop it. So they don't bounce off of each other well. There's not much you can tell. All I can say is it looks like the lighter mass does in fact stop. Okay, before it rebounds less than the other one, but it's not much of a difference. So, but this lighter one has to end up sort of, okay, by calculation fact, it has less total energy because it's a lighter object on the end of it. And the rest of the objects are the same. So we have 2 equal poles. One of them's dropped from 4 times the height. The other one's only dropped from 1 unit of height. So if you just did the experiment with the sticks themselves, and you had a super light thing here to hit with, you just bend the metal so the 2 poles hit each other. You could sort of understand that obviously the one pole that's 4 times the height is going to have twice the velocity and therefore twice the total momentum. So it's just sort of you're starting from that point, and you have to recognize that that's diluting your experiment. So again, this thing isn't a perfect lever, okay, and this thing over here is not a perfect string. It's not a weightless, massless object. Now it's really far. A string is pretty close to being ideal, but this is really far from being ideal. So you could sort of just understand, if I just had the two sticks with the same mass, that if this one's 4 times higher, twice the velocity, then obviously it's going to have twice the momentum when they hit. So it should, in a sense, cause more energy to go this way than it'll go back this way. That would make sense. Momentum wins. But because you did put a 5 mass here, okay, and a 10 mass here, to some extent, all right, this total mass now, say if this thing weighs 10, this total mass is 15, where this total mass is 20. So if you thought of it as a total mass, you're dropping a 20 from one distance and a 15 from 4 distances. Obviously this side's going to end up with more momentum. So, you know, obviously if you have a weightless string, then you're not diluting the experiment between the masses, because they're the only things accruing any velocity or any momentum. So it's the fact that this has a big chunk of momentum and this has a big chunk of momentum. They're the major players and these are the minor players, and they're just diluted by this extra mass. So again, you're back to the same problem I described with the lever, in the sense that you have to account for the fact that if you're using it as a catapult, okay, that the problem is you have to account for the momentum that actually goes into the lever. And so you don't have an ideal lever, so you can't strictly use a 2-to-1 distance ratio, because your real masses are the whole lever plus the object, not the masses themselves. So this ends up being, again, if this was 5 and this was 5 and this was 10, I mean this was 5 and this was 10, you can understand that there's 15 when it's this object, and there's only 10 when it's this object. Not 2-to-1. Yeah. So that's probably enough. Right? Don't really have to beat it to death. I'm trying to think of some, since you have this set up, some purpose or use for it. But at the moment I can't think of anything that would make it useful. So I'm, it's interesting, I suppose. I don't know. It just visually is a way of checking. So if you put your board behind it again, maybe you could get a visual of when you measure from the actual surface up. But then you have to make sure your surface is level and it's not bowed and all those kind of things too. So how perfect these measurements are is, who knows. So I don't know what to say on that subject. I don't know whether it's worth trying to convert it into an experiment. Maybe you could put something in between, where both of these objects hit that thing. You could put a lever in between. Just trying to think if there's some way you could put something in between the two, okay, that would absorb their opposite energies. But I don't know if that'll tell you anything either. Whoever hits first wins, essentially. That's another truth. It's not about having the most momentum, it's also having in this circumstance, causing action first. But anyway, I think that's probably enough. I don't think there's anything to make out of this one. Again, just goes back to the point that conventional physics should have already explained all of this. They should have already done all these crashes between different weighted objects. They don't have to crash 1-ton cars. They could do 10-pound cars. They could do lots of things and put test instruments and get exact ideas of exactly what's going to happen when two momentums or two kinetic energies interact with each other in an elastic way. And that's the better way to do it, obviously, because you want to keep all the motion in the objects. You want the two objects to keep the motion. You don't want it to disappear as heat or some other thing that you can't see. Obviously, in this case, because he's using, I think, soft steel, there's very little bounce, and so the energy is being converted into deformations and heat. The objects probably did get hot after impact. So anyway, enough of the video. So till the next time and such, so forth and whatnot.